So hopefully you see. No, sorry, I struggle here a bit. So now I'm ready. Oh, almost ready. So basically we have just a CNO cycle, how we come from carbon to nitrogen, or at least nitrogen here. Step on to oxygen, but then the oxygen 16 that we create in the state we created falls apart again. So this is good to create the nitrogen in between. And it's an energy production mechanism. At the moment, it contributes to the sun 2%. It's going to rise. For heavy stars, this contributes already much more. Now, the step to go further is basically carbon 12, helium. That's what we have just seen to fall apart. We can create it in other states. And then we build oxygen 16. Oxygen, of course, we want to have. From oxygen 16, we could have another CNO type cycle with proton captures. So to create fluorine and then maybe neon. But it can also proceed via, again, helium particle or helium nucleus for helium nucleus alpha particle capture and create neon. And from this neon, again, step on. And in between, we have, every time we have created one of these isotopes or elements, these act as another seed for CNO type cycle. Wow. Well, but since the Coulomb wall is increasingly higher, what happens? We have first an inert core of this ash. Not only of this ash, there is also, of course, loads of hydrogen still around and enriched in this ash, which is, even if it's created on the surface of the shell, is then slowly but surely sinking down. Now, what happens is then, because the mass density is now higher, it contracts basically a bit the center. And therefore, if it contracts, the pressure increases, and therefore the temperature increases. If the temperature increases, the Maxwell-Boltzmann distribution goes towards the right. What means suddenly we get, how to say, we get a sizable tunnel probability even for heavier elements. And if heavier elements then can fuse, well, what we get is, of course, always this binding energy per nucleon multiplied with the nucleon number. So each of these reactions produces much, much more energy than the PP reaction. What means there is also much more energy produced. It automatically gets hotter. In the moment this kicks in. So the first ones are basically igniter and then whoosh. What of course happens to the star is when you produce suddenly much more energy in the center, this is transferred to towards the outer layers, and what means it increases. But this also means there is no less pressure on the center. This reaction rate drops. And if the reaction rate drops, what happens? You produce less energy. The Maxwell-Boltzmann distribution shifts a bit to the left. You still produce less energy. The outer material falls, or it's not falling, but it comes back, increases the pressure. The Maxwell-Boltzmann distribution, it gets more pressure, it gets hotter, the Maxwell-Boltzmann, more tunnel processes, you produce more heat, the entire stuff starts again to, what happens is the star seems to pulsate a bit. When did we have this already? Exactly, Cepheid variable stars. the luminosity, what means the overall size, the frequency. Aha, now we have a mechanism. And it's basically that occasionally, well, what also happens is occasionally you enrich and enrich, enrich, and then above a certain pressure threshold, temperature threshold, you start to have to kick on the next reaction. And this is a successive step, but here then at some point also competing processes kick in. So for example, 24 magnesium alpha capture, we would be at 28 silicon. Now, people say also you can have carbon burning, that is carbon on oxygen, you create 28 silicon. But there again, the Coulomb wall becomes very high. And then, of course, 16 oxygen, there would be now in this reaction, this neutron evaporation. It creates 31 sulfur. That would be one of these. So there are plenty of reactions. In fact, this is a big, big network. Then one creates very high energetic light. Sometimes this light is so high, so energy rich, that it can ionize basically nucleus and take particles out of the nucleus, mostly neutrons. So becomes complicated. Well, in the last stages, people think that even very, very big stars where the pressure in the center is then super hot, that then the silicon might be able to merge. So fusion of two silicon nuclei, and then you see here the mistake. You start with 1414 plus 1414. To me, it's usually 2828 and not 2630. What one rather makes is 56 nickels, and 56 nickel then usually decays by a 56 cobalt. This decay has in the lab condition a weak half-life. But this is the only radioactive nuclear decay that we can modify at protons. Often not decay directly to neutrons. What they do is capture electrons. And now if we take the electrons away, this process is obviously basically a dietary for the protons can't eat the electrons and therefore not become neutrons. It takes longer. So there might be a hindrance because we don't have atoms at this point. We have a plasma. It's so hot, not many electrons are attached. So this decays to 56 cobalt, and 56 cobalt then decays to this 56 iron. And this has been indeed observed in gamma rays, that high energetic light that we would associate with 56 cobalt decaying to 56 iron has been observed in light curves of type 1a supernovas, or in one that wasn't too far away. And the light curves nicely go usually with the half-life. For the first 2 or 3 years, you almost have this decay 56 cobalt, which is 120 days or so. And then comes a longer lived 57 cobalt, because all the 56 cobalt has been transferred to iron. But then we have a problem, because, well, that is, well, first of all, what we see in the abundance pattern. So we would now expect always to have these steps with the alpha particle, like carbon to oxygen. In between, there's the C-No stuff. And now we see oxygen to neon. And in between, there's a bit of fluorine. Then from here to magnesium. From magnesium to silicon works. Then from silicon to sulfur. So we here see the spikes that we would associate with the alpha particles. Capture seems to work up to calcium 40. And then beyond calcium 40, the next element is not really stable. But this would radioactive decay before we can continue. So here we really need to go with the silicon burning towards this iron nickel peak. Oh, this is what a star can do. And then we get enriched in the center of this star, a core consisting at the beginning of iron, of nickel, and then slowly decaying to iron. In this process, producing a bit of energy, but not too much. So relatively inert core, and sorry, there is no ambulance driving by. Oh, it was firefighters. Okay, so we really see here this pattern, and we see here the beryllium barrier, triple alpha process to jump over. If you think about what you learned in the last 2 hours, how the elements up to iron are made, mostly. Well, and why does it stop with iron? Because iron 56, this is not exactly true. Really true is that nickel 62 has the highest binding energy per nucleon, so a bit higher than this here, but it's behind. So it can't really, the reactions from iron to nickel 62, there are, at least with protons, that the energy, what you gain from is basically negligible. But it's a common misconception. Iron 56 is not the most tightest bound nucleus. It's just that all these fusion processes end there. Because it's in this mass region where the binding energy per nucleon is highest. So from there on, we decrease. We wouldn't gain energy by fusing two nuclei. In fact, here above, we gain energy by splitting nuclei and bringing them closer in the mass ratio towards this area where we have the highest binding energy per nucleon. This is how a fission reactor works, so Hunterston. And here, this is hopefully in the near next 20, 30 years, a fusion reactor. Well, that would be very at the front towards basically the PP chain resembled, but they're deuteron plus tritium, so heavy plus over heavy hydrogen, but still has radioactivity involved. But this is energetically the reaction where we get most out. So hopefully the next 25 years, I think when I started studying about 25 years ago, fusion reaction was about, or fusion reactor was about 30 years ago. 40 years, it was about 30 years to go. 50 years, it was about 30 years to go. So there seems to be a constant. You plot the time and how long until the reactor is finished, which is relatively constant. My God, now comes the next motorcyclist. What is going on today? Okay, so we have seen already again a lot. And sorry, rearranging. And obviously the star is burning in different cycles. Every time he starts to ignite a reaction, this produces more energy, and then it cooks a while. But then, of course, at some point you might run out of fuel. At least you run low. Of course, what happens is in the shells above, you still have the burning going on. There might be migration of the newly formed elements into the shell where you consider this burning stage, or then in the end towards the very central. So what's happened is then when we produce so much energy, because we have now these very heavy elements fusing, or even the triple alpha process, we produce loads and loads of energy in the center. We make it very hot. This temperature is obviously then with time traveling towards the outside, making the outside gas out. So the non-burning envelope also gets hotter. What happens? The gas particles are moving faster, and therefore they have the high energy tail of the Maxwell-Boltzmann can now escape in the gravity field to cool down. That means the entire stuff is growing and growing and growing. The more you produce heavier elements in the center, the more energy produced, the more the stuff is growing. What you get is the star. Basically, when the triple alpha kicks in, starts to become a red giant. It leaves the main sequence. So if we have a really big star, well, our sun has only maybe, if at all, it makes it to oxygen. If we have a bit of a heavier star, it might make it to magnesium. And the burning towards iron, you need about at least 8 solar masses to have sufficient pressures and temperatures in their center to fuse anything so that in the end you come to iron. And so roughly then I think this is now relative to scale. So you see basically all the non-burning hydrogen envelope, then there is a bit of hydrogen fusion in the very center almost. And the deeper we go in the layers, the more heavier the elements. And then in the very center, what we get is this enrichment of a non-burning iron core. Iron is, of course, compared to 56 in a very small volume compared to 1. The volume is not so much bigger, so the mass density increases and increases, and therefore also the gravitational pull. Or if we just would take this sphere by itself, it has a gravity that tries to pull everything inside, and there is not much that works at the moment towards the outside. Oh. So the iron core keeps growing. And what happens after at a certain limit, we're going to talk next week when we talk about the death of stars, of massive stars, type 2 supernovas. Well, in fact, it's quite interesting if you look now in the different burning cycles, how long they take and what temperature is necessary. So if we have a star of 15 solar masses, our sun has in the center about 15 billion degrees, a million degrees, and this star has then 35 million. What means the Maxwell-Boltzmann distribution is shifted twice as high. Therefore, with this exponential increasing tunnel probability, the gamma of peak is much, much bigger. So this star would only burn 11 million years in the helium on the main sequence. Then now one assumes that the helium burning, what means the triple alpha process, we need already heavier temperature, hotter temperature of 180 million degrees. Only 2 million years, or now with the newest result from Tibor, it would probably just 1.5 million years. Then, once we have created the carbon ash, and the carbon ash is in the center and pulls a bit more, the temperature increases, and when it reaches, it's roughly 800 million degrees. We will have for roughly a couple of thousand years, 2,000 years, make there all some error margin, so plus minus 2,000 years. The carbon burning. And then we see once the carbon carbon-12 alpha gamma reaction happens. We have create oxygen. Then, well, the contraction is quite large. We get 1.9 billion degrees in the center of the star. And this is insufficient in relatively short time to create a couple of years to burn onto neon. And then less than a year at the lower temp, that cannot be, that must be 2.6, so probably I made a mistake when or the guy who made this table that I copied and pasted shamelessly somewhere. So now we are less than a year where the neon is burning, and then the silicon burning is a couple of weeks. So that's it basically, and this is 15 solar masses. So smaller star will of course take, this all takes longer, and for bigger one, what will happen? This goes much faster. And here basically, once this is the helium is exhausted and goes the hydrogen and goes to helium, it leaves the main parts. And then the red giant phase. So one of these red giants, well, Orion, the shoulder of it. This here is Betelgeuse, red giant, and this here is Rigel, a blue giant which is on the path. So Betelgeuse is already quite far advanced. In fact, Betelgeuse, we wait basically that it becomes a nova either tomorrow, or maybe if we get the light now, it's 500 light years away. It would have been, of course, 500 years ago. But we might see it tomorrow, or maybe in 100,000 years. That is not really clear. Yet Betelgeuse is very active, and it was a year ago or 2 years ago, Betelgeuse dimmed down. It's usually, I think, the 7th brightest star in the night sky. And one could really see with the naked eye, this is now much, much, much dimmer than it used to be. So even I could recognize this, then can't take that much. So Betelgeuse is very interesting nucleus, very interesting star, sorry. So then you see here Rigel, which is also already on the path. Oh. Okay. Well, what happens occasionally? This is quite interesting. Some of these big ones, they get rid of a lot of the hydrogen envelope. This is basically when one of these new processes kicks in. It goes relatively quickly that it kicks in. That means you have something like a shock wave going out. And if you had already a red or the outer envelope quite expanded, and now you have a shock wave coming from inside, it might be enough to push out the outer layers of this non-burning envelope. So sometimes it's sufficient that one basically gets rid of the hydrogen and has then just this core. Some of these very heavy stars, sorry, that I don't know what's at the moment and twisted in my mind that I constantly try to say nuclei. But you see here then Betelgeuse, Rigel as part of Orion. Next time you look up there, enjoy Betelgeuse, the night or afterwards it might be gone. To give you a feeling about the sizes, well, this Aldebaran is this guy, it's a red giant, but it comes from roughly the mass of our sun. Not too much, while Betelgeuse, I think, has 20-25 times the mass of our sun. I would have, but I'm not sure, I have to look this up. So in comparison to our sun, which is here, this little yellow dot, and which you might see or not. Aldebaran, which is a red giant. Rachel, which has already got rid of parts of its envelope. Then you have this Antares, and then you have basically Betelgeuse, and Betelgeuse is not even the biggest one. There are even much more massive monsters. But it's about 1,000 times bigger than our sun. Okay, and it's also pulsates already. That means it's like a bit like a Cepheid variable. It increases in size. The luminosity goes up when it increases in size, but then at some point it becomes a bit dimmer and it falls also together, or shrinks a bit in size. So it's basically also some kind of Cepheid variable. And this is now quite interesting, that if one looks here at the branch that leaves the main sequence, this is where we find basically these classical Cepheid variables. These are our Lyria star, these are Tauri. So basically here are what is leaving the main sequence from a heavier side. These are these standard candles. These become these pulsating variables. So Betelgeuse has a relatively long variability. Of course, it's very big, it's very luminous. So, okay, so if you remember the Cepheid variables, where the period was going on, and then we had this basically becoming bigger and very luminous and becoming smaller and less luminous. And this was going on periodically. Now we can understand what's going on. Okay, so basically the core contracts at some point, becomes hotter, denser, hotter, until we can basically, or the heat of this contraction, when it becomes hotter in the center, the heat always migrates from hot to cold, from a hot temperature, from a high temperature to a low temperature. This is how heat migrates. It's basically the gradient of the temperature difference. By the way, this is called Fick's law. And if you take a dictionary and look up after Eugen Fick, if you look up what Fick means in German, poor guy. He was not the luckiest with the name. Okay, so heat travels towards the outside also heats up and therefore expands. Okay, so the core becomes denser and hotter, but the outside becomes also hotter, but it can expand. So, of course, the expansion cools again the outside. That's why Betelgeuse is so reddish instead of being super blue, because it has no so massive surface. The same energy is now going to heating up a much larger volume, or even more energy. That means the center becomes hotter, but when you have a hotter oven, but now you basically put the oven not in your living room, you put it in a sports hall. Even if the oven is hotter, it is not capable to heat up the entire sports hall, maybe. Or if you're lucky, then it's possible. So I hope this helps a bit to get a feeling. Okay. Now, of course, the outer layers are now further away from the center of gravity. That means they are much looser bound. Well, what of course happens if the outer layers migrate away? The pressure in the core gets a bit less. Therefore, the temperature drops a bit, the reaction rate drops a bit. And What means to produce less heat. Less heat is transferred to the outside, and the outside might then say, oh, we shiver now, we want to go closer to the fire. And so the star shrinks again. If it shrinks again, the pressure in the core rises, the temperature in the core rises, the reaction rate rises, the production of energy rises. Oh, and what means we get now a self-controlling, pulsating nuclear fusion reactor. Or this is going on until, of course, it runs out of fuel, and then everything contracts even further until the next burning stage goes on. So we have this self-regulating, and we understand now what is going on in the C-fate variables. Or if you observe a pulsating star that is significant pulsating, you know it's in retirement, and soon it's going to interstellar hospice, like Betelgeuse. So its end is coming. Okay, so to summarize what we have learned today is basically how we start with hydrogen, a bit of helium, jump over this stuff here, lithium, beryllium, boron, to carbon. Then stars like our sun might carbon, maybe up to oxygen, if at all neon, but for everything else you need larger stars. And then we can burn up all this stuff all the way here up to iron, or in a star, when the star is still. Since we are mostly built of carbon and even heavier elements like calcium, iron in the red blood cells, we can very safely assume that each of the atoms in our body has been part of a star. So, sounds now, yeah, but when I was your age and somebody told me basically all the parts in your body were parts of a star, I found this quite fascinating. And with this, I would say it's now almost 3 hours, or probably 3 hours of stardust waffling. So enough for today. Next week, we look then what happens. Oops, the next firefighters. No. So next week, we look what happens with this iron core when it becomes too heavy. And also, how are these elements made? Going basically up from cobalt, nickel, or I should expand this stuff here, then up to even uranium. So these, most of them are made in the last days of a star and when it dies, or when the corpses merge. Depends on who you believe nowadays. So next week is about the dying of stars. See you then.